In this video, we're going to look at the band theory of solids, energy levels, valence band, and conduction band in solids, i.e. conductors, semiconductors, and insulators. In an isolated atom, electrons have specific energy levels. When atoms are close together, e.g. in solids, the single energy level in an isolated atom broadens out to form an energy band in a solid. An energy band is a range of allowed electron energies. That's an energy band here. We've got what's called a valence band, and then here that's a conduction band. So that's a range of energies. An electron cannot have an energy value which lies in the forbidden gap between the bands. So that's the forbidden gap here between the bands. We have the valence band in this diagram here shown in greenish yellow. And then we have this one in a peach color, which is the conduction band. So in conductors, the energy gap between the two is negligible. Therefore, the two, they overlap. As you can see, the valence band and the conduction band, they overlap. So electrons can jump from the valence band straight into the conduction band. Whereas in semiconductors, the gap is small so that some energy can be supplied to enable the electrons to jump from the valence band to the conduction band. And then in insulators, the energy gap is too large. Therefore, electrons can never jump to the conduction band. I've got a video to show this that I'm trying to put across. So that's the valence band that we start off with. In the valence band, we do have all these electrons in there. So when a certain amount of energy is given to the electrons in the valence band, they absorb energy and go to the conduction band, as you can see. The energy difference between the valence band and the conduction band is called the forbidden gap, like I talked about. Then for insulators, this forbidden gap is too large. The electrons can never jump. Then in semiconductors, the gap is small enough for the electrons to be given sufficient energy from the valence band to jump straight into the conduction band. Then in metals, there is negligible difference between the valence band and conduction band in energy. Hence, the jumping electrons from the valence band is easy. A little amount of energy is sufficient to promote this to take place. In a metal, the conduction band is partially filled. Electrons in this band can easily move to unfilled levels further up the band. This happens when a metal is connected to a cell. The electrons that have moved upwards are free to move through the metal, so there is a current. In an insulator, the conduction band is unoccupied, it is empty, and the valence band is fully occupied. An electron whose energy lies in the valence band is bound to an individual atom. There's a large energy gap between the top of the valence band and the bottom of the conduction band. The voltage of a cell is insufficient to lift electrons across the gap into the conduction band. Electrons are not free to move through the material. Hence, there is no conduction. Then in semiconductors, it's almost similar to an insulator. That is, the valence band is full and the conduction band is empty at 0 kelvins, that is. But the gap between the two is small. Therefore, at room temperature, few electrons have enough energy to jump across the gap into the conduction band. These electrons in the conduction band are negative charge carriers and can migrate under the action of an electric field. So we do have that. So the electrons that enter the conduction band leave a hole in the valence band, which acts as a positive charge, because now we have an excess of positive charges there than negative charges, since a negative charge has jumped and moved. So there's a deficiency here. So which means the hole that is left, the gap that is left, the void that is left is positive. So we call that positive hole. Under the action of an electric field, a neighboring electron fills the hole, creating a hole in its previous position. So the hole migrates through the solid and acts as a positive charge carrier. So if electrons move to the left, as shown by the arrow, positive holes will be moving to the right, because the hole constantly moves in the direction opposite to the movement of the electron that jumps. I hope that makes sense. The electric current in an intrinsic semiconductor above 0 kelvins is due to the movement of electrons, which are these negative charge carriers, in the conduction band and holes moving in the opposite direction to the valence band. So we have negative charge carriers, which are electrons, and positive charge carriers, which are positive holes. The number of holes in the valence band is exactly equal to the number of electrons in the conduction band. Then above 0, that is above 0 kelvins, the vibrations of the atoms in the lattice increases, and these vibrations hinder the movement of the charge carriers in the solid. However, the effect due to the increase in the charge carriers outweighs the effect due to the increase in the lattice vibrations, so the current increases and resistance becomes smaller. Now, this diagram that I'm going to show here, it's a graph that shows you how the resistance falls as the temperature increases in a semiconductor. It's curvilinear. Silicon and germanium are examples of intrinsic semiconductors which behave like this. However, in metals, the resistance increases when the metal is heated. Its atoms vibrate more at higher temperatures and hinder the movement of electrons. The current decreases and the resistance increases, but this increase in resistance is comparatively small. So there you are, you see. So current still flows in conductors. However, resistance will slightly increase. In a light-dependent resistor, that's an LDR, photons of light are absorbed by electrons in the valence band so that they can jump the gap and enter the conduction band. Hence, an LDR has high resistance in the dark but a low resistance in the light. I'm going to end the video here. So if you have any questions, please post them in the comments and let me know of any area that I need to revisit. Signing out.